Section 6.2, the definite integral and net change of a function. So, first off, let's suppose that f that we've had is a continuous function on a closed interval from a to b, with an antiderivative specifically being f. Then, the definite integral of f from a to b is defined notationally as, and we write the integral symbol, and then we give limits of integration, that is from a to b, of f of x dx. And the way that we actually evaluate this is we find the antiderivative of f of x, but we're going to ignore that constant c stuff. And we're going to find the antiderivative. Well, since the antiderivative is capital F, then you just take f of that upper limit of integration b minus f of a. And so this is what we are calling a definite integral. Now specifically, like I said, the numbers a and b are called the limits of integration, with a being the lower limit and b being the upper limit. And then the number f of b minus capital F of a can be thought of as the net change of the function capital F, which is the antiderivative, as x varies from a to b. And so that specifically is abbreviated by the symbol f of x, and you can draw a vertical line a to b if you so desire. Because when we're doing these things, you'll find that we need to find the antiderivative first, and then once we find the antiderivative, then we plug in from a to b, and so it's f of b minus f of a, and so this notation can be useful. Alright, so a handful of things that occur when dealing with definite integrals, that is, the integral of sums and differences is the sum and difference of integrals. And so this is the same thing as the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. We also know that the integral of a constant multiple, well, it directly applies to definite integrals, and so a constant times the integral from a to b of f of x dx. Something new and interesting, and that is if you wanted to switch the limits of integration, and there are some reasons to do this, but if ever you decide to switch the limits of integration, swap the a and the b, you can, but you just have to make the entire thing negative. So that's going to be negative from b to a of f of x dx. So you have this neat property with swapping the limits of integration. And so this next one, notice that we have the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Well, notice that the upper limit of integration b and the lower limit of integration b, they're the same. Well, because of that, you can push these two together and say that this is really the same as one single integral from a to c of f of x dx. And so these are just a handful of properties that may make life easier when we're dealing with these things. And then, of course, the definite integral as a net change of a function is like we stated before, that is the integral from a to b of f prime of x dx is equal to f of b minus f of a. And so I just changed my notation a little bit. Instead of using a lowercase f here, I'm using a capital F to show you that really capital F prime is what we're dealing with. So now let's evaluate some definite integrals. So then we have a definite integral, the integral from 1 to 2 of negative 3 over x squared dx. Well, I'm definitely going to rewrite it first, and so I see that this is the same thing as from 1 to 2 of negative 3 times x to the negative second dx. At this point, if you want, you could pull the constant out front, and this is the same thing as negative 3 times the integral from 1 to 2 of x to the negative second dx. Well, that's just going to be negative 3 times, now let's find the antiderivative of x to the negative second. But remember that that's going to be x to the negative second plus 1 divided by negative 2 plus 1. But then that other notation, we're going to have to plug in those limits of integration, so from 1 to 2. And so then this is what? This is negative 3 times x to the negative second plus 1 is x to the negative first, divided by negative 1, limits of integration from 1 to 2. Well, that's then going to give us negative 3 divided by negative 1 is positive 3, so this is 3 over x from 1 to 2. And so that's then going to be 3 over 2 minus 3 over 1, where you just plug in each piece. And so 3 halves minus 3 over 1, I need to find common denominators. So 2 over 2. 3 minus 6 is going to be negative 3 halves. And so that is our net change between 1 and 2 for the function 3 over x. And now we've calculated a definite integral. Now one more note, remember that because we are doing definite integrals, we won't have to indicate the c, or that constant, being added when we find the when we find the antiderivative. And so pay attention, because you will have to remember that when you take an indefinite integral, you do have to write that constant c for the antiderivative, whereas when we have a definite integral, you just get a numerical value. Alright, number 2. Note that I have a typo. I do need a dx. If I don't have the dx, technically it's wrong. So then the integral from 4 to 9 of square root of x plus a half minus x. Well, first things first, I can break this up into 3 separate integrals. And so I'm going to do some rewriting as I do this. Or you don't have to break up over all 3 pieces. That's really just a matter of preference. But I see that this is the integral from 4 to 9 of x to the 1/2 plus 1/2 minus x dx. I just wanted to rewrite that square root properly. Then when I use my general power rule for each one of these, this is then going to be the antiderivative of x to the 1/2 is going to be 1/2 plus 1, or x to the 3/2 divided by 3/2, plus the antiderivative of a constant is the constant times x, so that's going to be 1/2 x, minus, and this is going to be x to the 1 plus 1, or 2, divided by 2, and our limits of integration are from 4 to 9. Well then, what's this going to look like? This is going to be, going to deal with this 3/2 is really the same thing as 2/3 times x to the 3/2 power, and so then that's going to be 9 raised to the 3/2 power, plus 1/2 times 9 minus 9 squared over 2, and then subtract, and when you subtract all of this, make sure you put a bracket. That's going to be 2/3 4 raised to the 3/2 power plus 1/2 of 4 minus 4 squared over 2. Well then, the square root of 9 is 3. 3 cubed is 27, and so this is 27 times 2 divided by 3, but 27 divided by 3 is 9, and so this is 18, plus 9/2 minus 81/2 minus, we do have to be careful here, so this is the square root of 4, which is 2. 2 cubed is 8. 8 times 2 is 16, so we get 16/3, plus 4 divided by 2 is 2, minus 4 squared is 16. 16 divided by 2 is 8. So subtract all of this. And so let's rewrite this. And so 18 plus 9/2 minus 81/2, that gives me negative 18. And then minus negative 2/3. Negative 2/3. And so this I get is negative 18 plus 2/3, which is negative 52/3. And so that is the amount of change that occurs over the function as we move from 4 to 9. Alright, so now we're just playing with some of the properties of definite integrals. And so notice that the first thing we're told is that the definite integral of f of x between negative 0.5 and 3 is 0. And then we're told that the integral of negative 0.5 to 3 of 2 times gx plus f of x dx is equal to negative 4, and we're supposed to find what is the definite integral of g of x between negative 0.5 and 3. This is really just a complicated looking algebra problem. That's all. So we do have to use some properties, but remember that the integral of sums is the sum of the integrals. And so this, I'm just working with this right here. And let's see what we get. Well, I can go ahead and take a constant times a function. And so this is going to be 2 times the integral from negative 0.5 to 3 of g of x dx plus the integral from negative 0.5 to 3 of f of x dx is equal to negative 4. Alright, at this point, note that the given was that that definite integral equals 0. And so that means that this really states that all of this is 0. That's it. So then we get that this is 2 times the integral from negative 0.5 to 3 of g of x dx is equal to negative 4. Okay, but then we can just do algebra and then kind of leave the integral by itself, divide by positive 2, divide by positive 2. I then get the integral from negative 0.5 to 3 of g of x dx is equal to negative 2. And we're done. That's all we needed to find. What was the definite integral of g of x? But recognize that the first step I made was separate integrals over sums, and constant times a function inside an integral is the constant times the integral of the function, and that allowed me to treat it algebraic. Alright, let's see if we can do it again. So here we're given that the integral from negative 3 to 2 of f of x dx is equal to 10. And the integral from negative 3 to 6 of f of x dx is equal to 15. And we're supposed to find the integral from 2 to 6 of f of x dx. Well, recognize that this property is the integral over adjacent intervals. And notice that we get negative 3 up to 2 and then up to 6. Alright? And so we can use these three numbers to break up our intervals. Alright, so let's see how we do that. Well, if we know that the integral from negative 3 to 6 of f of x dx is equal to 15. Well then, what can we do? We can break up this integral. This is then the same thing as, well, I want to break it up as the integral from negative 3 to 2 of f of x dx. So the integral from negative 3 to 2 f of x dx plus the integral from 2 to 6 of f of x dx is still equal to 15. All we did was cut up that interval between negative 3 and 6 to be from negative 3 to 2 and from 2 to 6. So we're using that integral over an adjacent interval property. Well then, we're told something. What are we told? The integral from negative 3 to 2 of f of x dx, right here, is 10. So then I get that this is now, this part is 10, so 10 plus the integral from 2 to 6 of f of x dx is equal to 15 minus 10 minus 10. I then get the integral from 2 to 6 of f of x dx is equal to 5. That's what we tried to answer. That's what we were trying to answer, and so we are done. 5 is the answer. Alright, so for this next one, we're told that f prime of x is equal to 73. And we want to compute f of 4 minus f of 2. And so notationally, what we're really doing here is we're saying, oh, well, I know that the integral undoes the derivative, and so I'm going to take the integral of f prime of x, but from where to where? So specifically, I want to go from 2 to 4, because that's what's being plugged in, dx. And this will actually give me f of 4 minus f of 2. So notationally, this is what we got going on. Well, but to do this, I need to recognize that, of course, my f prime is 73. So this is the integral from 2 to 4 of 73 dx. And so the antiderivative of 73 is going to be 73x. And then we have to evaluate from 2 to 4. And so this is then 73 times 4 minus 73 times 2. And so I get 146. Okay. So, application problems. A rock is dropped from the top of a 400-foot cliff. Its velocity at time t seconds is v of t is equal to negative 32 t feet per second. We want to find the displacement of the rock during the time interval from 2 to 4. Now, the best part of this is that since we were given velocity, recall that previously we talked about the position function, s of t, and then if we wanted to find the velocity function, v of t, recall that v of t was equal to s prime of t. And so remember that our position function actually gives us displacement, whereas the velocity function gives us velocity, right? Well, recalling the relationship between position and velocity, being derivative to go from position to velocity, we can now go the other direction. If I want to get the position function, I can take the integral of the velocity function and get exactly that. So, we want to find the displacement. Well, that's going to be the integral of my function, my velocity function, negative 32t dt. But because we're looking for specific displacement on a specific time interval from 2 to 4, I'm going to take that integral to be from 2 to 4. So I'm going to take the definite integral. Well then, this is, find the antiderivative of negative 32t. That's going to be negative 32 times t squared over 2 from 2 to 4. So that is negative 16 t squared from 2 to 4. And so then we just evaluate this, negative 16 times 4 squared minus negative 16 times 2 squared. This is then going to give us, well, 4 squared is 16, negative 16 times 16 plus 16 times 4. And so this is negative 256 plus 64, which I get to be negative 192 feet. Now, if you're concerned about that displacement being negative, I'd like to state that what happened, a rock is dropped from the top of a cliff, and so velocity pulls it down, and therefore the distance from its initial location is a negative 192 feet below its starting place. Consider the marginal cost function, 0.09x squared minus 4x plus 100. If we want to find the additional cost incurred in dollars when production is increased from 3 units to 19 units, and we know that C of 3 is 254, we're going to help use this answer to find C of 19. And let's recall that marginal cost is literally C prime of x. And so marginal cost being C prime of x, we're told that C prime of x is 0.09x squared minus 4x plus 100. And so my claim is that my net change or additional cost is going to be equal to C of 19 minus C of 3, which notationally is the same thing as the definite integral from 3 to 19 of my marginal cost function, because of course that is the derivative of the cost function, so it's 0.09x squared minus 4x plus 100 dx. And so then if I want to find this antiderivative, this is going to be 0.09 times x cubed over 3 minus 4 times x squared over 2 plus 100x, and from the limits of integration 3 to 19. Well, 0.09 divided by 3 is going to be 0.03 times x cubed, or 19 cubed, minus 4 divided by 2 is 2, 19 squared, plus 100 times 19 minus C of 3 is what we should be getting here, which is specifically going to be 0.03 times 3 squared, 3 cubed, minus 2 times 3 squared, plus 100 times 3. And so I get that this is 205.77 minus 722 plus 1,900 minus 0.81 minus 18 plus 300. And then finishing off this arithmetic, make sure you distribute that negative. I get that this is 1,196, which then, let's pretend for one moment that we know that C of 3 is 254. Well, since C of 19 minus C of 3 equals 1,196, Supposing we know that C3 is 254, then C of 19 minus 254 is equal to $1,196. If that's the case, you could add 254 to both sides. Add 254 to both sides. And so we can get that in this instance, C of 19 would equal 1,354.96.